So what is nuclear energy exactly? We know that these nuclear power stations, okay, are going to be producing electricity. Now, how do they do that? Okay, so yesterday we were talking about, and the day before actually as well, we were talking about generators. One second, let me flip my camera. So we were talking about generators. Okay, now what a generator does is a generator is going to be converting an external force into electricity. That's what a generator does, using the generator force, the generator effect. Okay, now how the generator effect works is there's going to be an interaction between metal coils, like metal wire that's coiled around itself, and the permanent magnetic field around them. Okay, now if they're just sitting there, nothing's going to happen. There has to be movement. Those coils have to be breaking the permanent magnetic field. Okay, and as they're breaking it, it's going to lead to a movement of electrons, which is going to induce a current in the wire. That is electricity, okay, a specific voltage. Now, how we get that force to move the coils, okay, is where nuclear energy comes in. Now, we don't just need nuclear energy, we can use wind, okay, so wind farms are going to provide that force, as well as water, okay. So these are probably the two renewable ways and environmentally friendly ways that we can generate electricity, okay. There will always be wind, and there's always going to be a flow of water. Remember, this can be tidal as well, it doesn't just need to be these hydroelectric dams. Now, another way that we can do it, if we don't have wind or we don't have water, okay, we can use the movement of steam, okay. So, water vapor. Water that has evaporated is going to become this gaseous state called steam. That steam can also be used to turn these turbines and generate electricity. But how are we going to heat the water? Where are we going to get the steam from? Now, it's pretty cool. Some countries have these geysers, you can call them geysers as well, these underwater geysers, where it's naturally heated water that is heated by underground volcanic activity. And that water is going to generate steam. You just put a turbine down there and it's going to turn the turbine, which is really cool. Totally natural, okay? But if we don't have a geyser, we can use coal. Okay, so a bit archaic, a bit old, and not too great for the environment, but we can burn coal and then we can use the energy released from that chemical energy stored in coal to heat the water, creating steam, turning the turbine, creating electricity. Now, a more modern approach, but still pretty archaic in the fact that we're just using this generator technology, is that instead of using coal, we can use nuclear energy. Okay, now what is nuclear energy exactly? Nuclear energy deals with atoms, specifically splitting and breaking atoms in a process called fission. Okay, so fission is when an atom splits apart. Okay, now these fission reactions are going to release a lot of energy. Okay, they're also going to release neutrons. Okay, now what is a neutron exactly? Atoms are made up of protons, neutrons, and electrons. Okay, an atom with a specific number of protons is going to be called an element. Okay, if we change the number of protons, we're changing the element. Okay, we can change the number of neutrons, and that's going to give us isotopes. Now remember that word, isotopes. Okay, we're going to come back to that later when we're talking about uranium enrichment. Okay, so changing the number of neutrons is going to change the number of isotopes. Oh, sorry, it's going to give us different isotopes of a specific element. Okay, now, if atoms are too big, if they have too many protons, too many neutrons, they become unstable. Okay, and they will sometimes split by themselves, okay, and release this energy. Okay. Now, this is what we call radioactive decay. When we say something is radioactive, we're saying that it is unstable. It releases energy by itself as it sits there, because its atoms are slowly breaking apart by themselves, okay, and releasing this energy. Now, there are tons of radioactive materials on the periodic table, all of these at the bottom here. And why? Because they're so big. Now, the one we're talking about today is going to be this one over here, uranium. Okay, so uranium has 92 protons, okay, and an average atomic mass of 238. So, how does nuclear energy work? Again, we're just using this energy that is given off by these radioactive elements to heat water and to make steam and to turn a turbine. Okay, but instead of using coal, we're going to be using uranium. Okay, now uranium doesn't give off carbon dioxide, and the only possible byproduct of this is steam, as well as radioactive material. That radioactive material has to be stored and processed somehow after it's used, and that's another discussion for how well people actually process it so that it's safe to be disposed of. Okay, but let's see, how do these nuclear reactors work? So nuclear reactors are going to be made using three parts. There's a bit more, but basically three parts. Okay, we're going to need fuel rods. Fuel rods are going to be our radioactive material. Usually uranium-238, which is one of the isotopes of uranium, is going to be mixed in with uranium-235. Uranium-235 is a smaller uranium isotope, but it's a bit more volatile. It takes a lot less for it to split. Okay, we'll get to that later as well in a bit more detail. But uranium is going to then split in these fuel rods. As it splits, it releases energy, which is going to be used to heat up the water into steam. It's also going to release a neutron. Now that neutron carries energy. And when you've got another uranium atom sitting next to it, almost ready to break, and you hit it with a neutron, it breaks. And so energy gets released, more neutrons get released, and a chain reaction occurs. And this is why nuclear energy just carries on, and something will just be radioactive, because there's actually a chain reaction occurring inside of it. Okay. Now, if we want to control this reaction, okay, let's say that we run out of water. Let's say that we want to produce more steam or less steam, more or less energy. We need a way to control this reaction. We need a way to stop these chain reactions from happening. We're going to use something called control rods. Usually they're made up of carbon, because carbon is quite stable. And what's going to happen is these control rods are going to be put in between the fuel cells. And they can be lifted up or put in. And they are going to absorb the neutrons given off by the fuel rods instead of them hitting into another uranium atom, thus preventing this chain reaction and slowing down the amount of radioactive decay that is happening in our nuclear power station. You see that? Now, another thing that is going to be encasing this entire, this entire reaction, okay, is going to be something called a moderator. Now, a moderator is usually just concrete, and what that's going to do is it's not going to stop the neutrons, but it's going to slow them down so that it's a bit more efficient, and they're going to hit into other uranium atoms instead of going off in another direction. Okay, so fuel rods are the uranium that is decaying. It is breaking apart. The control rods are going to be preventing this chain reaction from occurring by absorbing neutrons given off by the fuel rods. Moderators are going to slow down the neutrons and make the process more efficient. Does everyone understand this? Now, this radioactive decay that we're talking about can also be used to date objects, to see how old objects are. You must have seen sometimes when they're talking about an archaeological object, and they say, this is over 20,000 years old. And you're like, how do you know? Were you there? No, of course not, right? No one was there so long ago, but somehow they're able to know its age. This is where radioactive dating takes place. So we're using it on inorganics, use carbon dating for organic molecules, but for inorganics like rocks, we use uranium dating. Okay, it's usually going to be the uranium-238 that decays into lead-206. Now, depending on the ratios of uranium to lead, we can tell how old a rock is based on the half-life of uranium-238. So we don't know when an atom of uranium is going to decay, but we do know how long it takes for half of the atoms in a given substance to decay. So by finding the ratio of uranium to lead and knowing the half-life of uranium, we can calculate sort of how old the rock is. Okay, so a more newer rock will have more uranium in it than lead, while an older rock will have less uranium and more lead. Everyone good? And so let's get started on today's topic. So we were talking about the fact that for nuclear energy in these nuclear power stations, we're going to need uranium. Now I'm going to give you a full breakdown on how uranium is extracted from the earth and how it is processed into something that can be used. Now what it's used for is exactly why Israel and Iran are fighting each other at the moment. And that's up for debate. But I'm here to tell you what their reasons are, supposedly. Okay. I think I can take this off. I'll do a quick rundown on it. So transformers, when we have this huge amount of electricity being produced by the power stations, it needs to travel over a long distance. So we need to increase its potential difference, the voltage, and we use something called a step-up transformer. So it goes through these coils. These coils, using the generator effect, are going to induce a current in a larger set of coils. We call it the secondary coil. It has more coils. We call this step-up. Okay, increases voltage so that less energy is lost during transmission. You must have seen these big power stations or these big towers that carry the electricity over long distances. There's a very, very high voltage in those things because it has to travel over such a long distance and try and lose as little energy as possible. But we can't have that massive voltage going into your house, because if someone sticks their finger in a plug, it's going to blow up the house instead of just give you a shock. So we're going to use a step-down transformer. A step-down transformer, lots of coils in the primary coil, inducing a lower potential difference in the secondary coil because there's less coils in the secondary. And then that can go into your house. Okay, on your phone chargers, I don't have one here. On your phone chargers, you can see there as well. Input will be 240 if you're in the Middle East, and then your output is going to be whatever that device needs. And that's why it's not a good idea to charge your phone with just any charger. I know Apple, makes it super expensive for a charger, and you might be like, the petrol stations one will work, but that petrol station's output might not be what your phone requires, and it may damage your battery because of that. So just keep that in mind. Okay, I think I'll take this off and we can talk about uranium now. Okay. Can anyone tell me in the comment section, where is uranium mined? Where do we get uranium from? What are some of the top countries in the world for uranium mining? Does anyone know? I think someone said that Iraq has some uranium mines before. And yes, we love you, my little Iraqis. Where do we get uranium from, guys? Also, by the way, just for anyone new here, we're part of Fame in Education. We don't make mugs, we make dreams come true. No, I'm joking. We are a tutoring company. Okay, a tutoring company based in Abu Dhabi. If you would like any help with your sciences, math, business, economics, programming, computer sciences, English, give us a message. We can help you out. Okay, so we have online classes as well as in-person classes if you are based in the Emirates. So if you're in Dubai or Abu Dhabi, we can come to you and have classes. Okay, otherwise, we do online classes as well. So give us a message if you need help in school, and yeah, we'll sort something out for you. Okay, go check us out on YouTube as well. I'm going to be posting more videos on there soon. I'm just learning how to edit these things. Yeah, okay. So let's see, uranium. Uranium is an element. We know that, okay? It can't be broken down into these smaller parts. It's an element. One atom that is going to have 92 protons. But it is not found in nature as an element. As all of you Minecraft people will know, if you mine an ore in Minecraft, it has to be processed before you can make something like a sword out of it. Okay, so it all starts out with uranium ore. So uranium ore is going to be mined mainly in Kazakhstan. So most of uranium is made in Kazakhstan. Sorry, I'm getting a call from someone. Jeebly, I don't know who you are. So most of the uranium ore in the world is made in Kazakhstan. Okay, the next one is Namibia, and then Canada. Some of my followers have also told me that Iraq has some uranium mines. Okay, so uranium ore is mined mainly in Kazakhstan, Namibia, and Canada. Okay. So this uranium ore now needs to be processed, but unlike Minecraft's iron or copper or something like that, it can't be melted down and then separated. We have to use acid. So this uranium ore is going to be treated with specifically sulfuric acid. Now this sulfuric acid is going to dissolve the uranium and not the rock. Rock is made mainly out of silicon. Okay. Rock is mainly made out of silicon. Okay. And so it doesn't react with acid. That's why when you get an acid, it's usually going to be in a glass container or something like that, right? Because it's unreactive. So this is called acid leaching. Cool. So once we have this now, it's going to turn into something called uranium trioxide. Now, some of my higher students will know that this is going to look like uranium O3. See, uranium trioxide. Hope you guys can see this. Yeah, I think you can. Yeah? Okay. Now, uranium trioxide needs to be processed into uranium dioxide. So, this is where some of our previous lessons are going to come in handy. How does uranium dioxide come from uranium trioxide? Or how do we get uranium dioxide from uranium trioxide? Does anyone know what this process would be called? This, people, is a reduction reaction. Okay, it is being reduced. And how we do it is we have to add nitric acid, so HNO3, plus ammonia. And this is going to lead to a reduction reaction. What is reduction? Okay, oil rig. Reduction, a gaining of electrons. And you might say, how am I meant to know that it's gaining electrons? Let's look at the charge of uranium in each case. So over here, it's going to be uranium. Each oxygen has a charge of -2. So that means that with 3 oxygens, it must have a charge of -6. Which means that uranium, to balance that out, needs a charge of +6. So it goes from uranium +6 into, over here, oxygen, only -2. So that means that oxygen, there's only two of them, so -2, it's going to have a charge of -4, which means uranium must have a charge of +4. So you see what's happening here is we're going from a uranium +6 to uranium +4, which means we've gained 2 electrons. A gain in electrons is going to be a reduction. So we have a reduction reaction from uranium trioxide to uranium dioxide. I'll just write it underneath here. You guys understand this? Thank you for the rose. I appreciate it. Now, this is where the good stuff happens. Okay, now, we were saying earlier that uranium is going to have isotopes. Now, this is important to know. You can have something like uranium dioxide, that is uranium-238 or uranium-235. Okay, so this uranium now can either be uranium-238 or it can be uranium, I'm actually going to write it on the other side here, sorry. Or maybe not, let me write it here. So it can either be uranium-238 or it can be uranium-235. So in this uranium dioxide, it can be one of these two isotopes. There's more isotopes, but uranium-238 is our most common isotope. Okay, so around, I think it was like 70%. Okay, there you go. 99% of uranium on Earth is going to be uranium-238. While uranium-235 is only going to be around 0.7% is uranium-235. Now, when it comes to isotopes, a lot of the times your more stable isotopes are going to be more abundant, which makes sense, right? Because the more unstable isotopes are going to be less because they are degrading quicker. So, the number of protons and neutrons for this, okay, so both of them, the protons, are going to be 92 because it is uranium, right? But the number of neutrons for each one is going to be, I believe, 146 in uranium-238, and over here, 143. You see that? Isotopes. Okay. Now, when it comes to the point here, and the point that it always should be, is that we are trying to get uranium into something that is usable for nuclear energy, okay, to create electricity. We're not trying to get it into a form that can be used for a nuclear weapon, ever. We are trying to get it into the form that can be used to generate cleaner electricity. Okay. So how do we do that? Well, first of all, this, we can say here, requires less energy to break. So 235, we said, is more reactive, okay, more readily breaks apart and fissions, okay. So, let me see here, cool. If this is more reactive, we do need a bit of it. We do need a bit of it to actually react, to start reacting, okay. But we don't need a lot. In fact, when we're trying to make nuclear reactors, we can say, now this is the important part that we're going to have to understand, and this is where Iran and Israel start to differ and where they start to fight about. Nuclear fuel rods, okay, require, how much is it? I think like 3 or 5%? 3 to 5, okay. 3 to 5% uranium-235, okay. But weapons grade uranium requires 90% uranium-235. They're trying to just make as big of an explosion as possible. So why would you need much 238, right? You want it to be as highly concentrated in uranium-235 as possible to make a bigger bomb, which is wrong. Okay, you only need 3 to 5% uranium-235 to make a nuclear fuel rod that will power thousands and thousands of homes. Okay, clean energy, sort of clean. Okay, so how do we get this 235? So it's not going to be feasible to mine it because only 0.7% of uranium mined in Earth is going to be 235. So we can process it. We can process uranium-238 into uranium-235. Now, if any of you guys watched Oppenheimer, okay, Oppenheimer's about it. So first what we're going to do is we're going to convert uranium dioxide into uranium hexafluoride. I think I spelled fluoride wrong. No, I got it. Okay. So uranium hexafluoride, UF6. It's a gas. Okay. Uranium hexafluoride is a gas. Now this part here is what we're going to call enrichment. So this is the enrichment process that we're going to need. So enrichment is going to be taking uranium 238 and converting, or not converting it, into uranium 235. That's uranium enrichment. Okay guys, so how do we do this? We're going to make the gas, thanks for the gift. We're going to make uranium into a gaseous form. Why do we want it in a gaseous form? Because it's super simple. We're going to be splitting these atoms based on their size. That's all. That's uranium enrichment. Uranium enrichment is basically just concentrating the amount of 235 that we have in a lot of gas of 238. That's all. We're not converting it. You see, that would take so much energy. That would take so much effort to just knock off neutrons from 238. Okay? We're just going to separate them based on their size. Now, Oppenheimer, during World War II, okay, the way that they enriched this in the Manhattan Project is they used a membrane. Okay, so they used gas diffusion plus a permeable membrane. So a membrane is something that's like a skin. Thanks for the gift. It's like a skin, okay? A divider. And this membrane had holes going through it. Holes that were just big enough to allow a uranium atom through. But because uranium-235 was smaller than uranium-238, it went through first. And therefore they were able to separate them based on the speed at which they went through that membrane. Okay? So we can have a uranium, a little membrane like this, with a bunch of holes through it. And we can just make, I'm going to put U235, 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 and then we have, let's say, one U238 with a bit more U238 here and U238 here. Okay, so that's what they would do. They would run this uranium hexafluoride through the membrane, and uranium-235 would be the first one to come through. And therefore they just collected it, and boom, they have enriched uranium now. They did that a couple times with 700 membranes, and that would get you this concentrated uranium-235 that they would then solidify to put into a bomb, unfortunately, for the Manhattan Project. But they realized that they could solidify it, and with a lot less of it, create clean power and clean energy, which is amazing, right? You guys still okay? You all good? My little Iraqis. Hope you guys are understanding something here, or at least enjoying the show. Cool. Now, this was during the Manhattan Project, long ago, not too long ago, but still, long ago enough that there is a modern way of doing it, a bit more efficient. Alright, here. So the modern way is that we use a centrifuge. Now, a centrifuge basically just means something spinning extremely fast. A machine that spins extremely fast. And these machines are usually going to be used to separate things based on their weight. Okay, sometimes based on their density as well. Okay. So it's basically cylinders that spin fast, very fast. And what's going to happen is these cylinders are going to have our uranium hexafluoride being pumped into them, okay? And they're going to have a little fan sort of thing like this. And what's going to happen is your uranium-235s, I should change this. So uranium-235 is purple, uranium-238 is going to be pink. Okay, uranium-238. What's going to happen is your uranium-238, because it's heavier, is going to move to the outside of this centrifuge. While your lighter uranium-235 is going to move a bit less further out, and it's going to collect in the middle. And there will be little holes in this sort of fan thing, and these holes are going to allow the uranium-238, or sorry, the uranium-235 to be collected. So we can say collection of uranium-235 from the center of the centrifuge. So that's the modern way that we do this, is using these centrifuges. They're long cylinders, okay, and they pump this uranium hexafluoride, thanks for the roses, into the centrifuge, and that's going to allow, I thought my mic had died and all of this hadn't been on. No, we're still good. Okay. And that's going to allow us to sort of purify, to enrich the uranium, to increase the percentage of uranium-235. Uranium-235 being the one that has more energy, uranium-235 being the one that can be split easier. Now, a mixture of uranium-235 with uranium-238 is what determines whether it's nuclear fuel rods or weapons-grade uranium. Okay, weapons-grade uranium will have 90% 235, while nuclear fuel rods will have 3 to 5% 235, because that's all that's needed. Thanks for the gifts. Now, where does Israel and Iran play into this? Okay, now, Iran, for many years, has been trying to get a nuclear program started, because they say, listen, I just want to make clean energy. They say that. Again, take everything I say now on with a pinch of salt, because we don't actually know what anyone's doing or what anyone's actually saying. Okay, so Iran says that they are trying to make a nuclear program to make clean energy. So they have set up a bunch of these nuclear reactor sites to enrich uranium. They bought uranium hexafluoride gas from some other country. They bought these long cylinders and they started making it. Now, America says, no, Iran, you're using it to make nuclear weapons. You're not allowed to do that. And for the longest time, they fought about that, and eventually Iran was like, fine, I won't have a nuclear program then. Recently, I don't know when, maybe in the last year or two, Iran was like, no, I'm going to make my nuclear program, and I'm going to start enriching uranium for nuclear energy, not for nukes. And you might say, well, how do you know? How do we know that they aren't enriching it for nuclear grade uranium, right? What it's going to be is that they can get inspected. Nuclear sites, the enrichment sites, can be inspected by the International Atomic Energy Agency. They don't belong to a country, supposedly, and they come in and they go, let's have a look at your uranium. What is the percentage of uranium-235? Because that's it, right? If you can prove that you don't have uranium-235 over a certain threshold, they're going to go, fine, let's do it. You don't have nuclear grade uranium. You're not enriching for that. They can also inspect the facilities that are enriching this. And by inspecting it, they go, there's a lot of centrifuges here. And that means that you're making very concentrated uranium-235 here. So therefore, you must be making weapons-grade uranium. So this is what they can do. Now, they did go to Iran. And this is just from the research I've done. I could be wrong. They did go to Iran, okay? And they found that Iran had 60% enriched uranium, which kind of means that it's higher than it needs to be for a nuclear energy, but not quite weapons-grade uranium, but very close to weapons-grade uranium. So they were like, and Iran was a bit seedy about it, was a bit sketchy, and they weren't giving all the documents or all the data, and there were some sites that didn't have the radioactive material that they should have, because all sorts of things. So they're not totally wrong here, but they weren't too clear with their products from these nuclear enrichment sites. Now that was enough for Israel to go, that's it, you've definitely got weapons-grade uranium, we're going to bomb you. And that's exactly what they did. Israel bombed the, what was it called? Okay, the Natanz enrichment facility was bombed by Israel. Because Israel said, yep, that's where you're making it, that's where you're making weapons-grade uranium. Okay? Now, the International Atomic Energy Agency said, Israel, what the hell are you doing? You can't be bombing uranium enrichment sites. Because imagine you bomb the site, it blows up, and now you've got uranium hexafluoride gas in the atmosphere. It's going to be dangerous. You see, so you're not allowed to bomb nuclear facilities. That's what they say. In the world, Russia and Ukraine, I don't know if they do, but they shouldn't be also bombing nuclear facilities, or they don't directly target them. But Israel has, and that's a bit of an issue. Okay. So guys, I hope you all understand a bit more now. This whole thing, I know it's a lot, but this is uranium enrichment, and this has led to war, which is a bit crazy, because let's say the Manhattan Project or Oppenheimer had just tried to make nuclear energy instead of a bomb. I think someone would have probably made a bomb eventually, but still, this is possible. And it's possible with a lot less. You see, this is what I want to get across to you guys, is that it's a lot more hassle, it's a lot more effort to make weapons grade uranium. We only need 3 to 5% uranium-235 to power houses with clean energy. But instead we go through the processes and we put so much money and so much resources into making weapons grade uranium that, alhamdulillah, luckily hasn't been used since World War II. But then for what? Don't do it. You know? It's ridiculous. It's not necessary. So yeah, this is it, guys. But politics aside, the science part of it is enrichment of uranium is done by separating them based on their masses, based on the size of the atom. Which is crazy. No crazy chemical process. No, it's the same thing as floating, or almost like floating ice in some water. It's just the size of the atoms. Okay. And what's going to happen when they get centrifuged or put through a permeable membrane? Okay, guys. So uranium ore dissolves by leaching, okay, acid leaching, to get that ore, the uranium out of that ore. It turns into uranium trioxide. That trioxide needs to be reduced, gains electrons, loses an oxygen to create uranium dioxide. Now, isn't that cool? I'm sure the byproduct of this is probably oxygen and water or something crazy. It's probably some nitrogen as well. But anyway, this uranium dioxide now can either be containing the one of two isotopes, okay? And depending on the percentage of that isotope, it gives us a different use for it. Okay, and that's why we've got war in the world, which is really sad. Anyways, so we're Feynman Education. If you want to watch more videos about topics like this, about physics, chemistry, biology, go subscribe to us on YouTube. Okay, we're going to be releasing a lot more videos soon. I'm just learning how to edit. If you guys have any editing software that you find is really easy to use, mention it in the comments for me. Okay, I'm also possibly looking for a way to translate my TikToks and my videos into Arabic or into other languages for that matter. So if you guys know of any software, any ideas of how I can translate these videos, let me know. And yeah, that's all I can think of. I'll see you guys in the next video.